In this problem, it says a farmer wants to fence an area of 24 million square feet in a rectangular field and then divide it in half with a fence parallel to one of the sides of the rectangle. What should the lengths of the sides of the rectangular field be to minimize the cost of the fence? One thing here, it talks about the cost of the fence, but we don't have any information about how much the fence costs per foot or anything like that. So minimizing the cost of the fence, that's really just going to be then to minimize essentially how much fencing there is. So how much total fencing we would have. In a problem like this, an optimization problem, there's a goal that we're trying to achieve, and that here we're trying to minimize the cost. So we're going to have to come up with a function for the cost. We can call that Q. That's the quantity that we're trying to minimize. And we're going to have to express that in terms of some other variables in the problem. One of the things here to sort of set this up, I really need a picture of the situation. So when I look at this here, we've got a rectangular field, it says. So we're going to have a rectangular field, something like that. And then it says it's going to be divided in half with a fence parallel to one of the sides. So I could set it up this way if I want. There's another fence. It doesn't have to be exactly in half, actually. It really doesn't matter where that fence is as far as how this problem is going to work. So what I'm trying to do is minimize the total amount of fencing. Well, I'm going to have fence going across the top, fence going across the bottom, and then these three vertical sections of fence. So I'm going to have to express those with some variables. Now, the three going up and down here, those are all the same length. I can use the same variable for each of those. I can call each of those lengths maybe x, and then I can go all the way across the top, and I can call that length y, and all the way across the bottom would be y. And so what I'm trying to do here then, I'm trying to minimize the total amount of fence. So I'm trying to minimize a function q. Well, what is the total amount of the fence? Well, there are three sections of length x and two sections of length y. So I'm trying to minimize this function q, which is 3x plus 2y. The problem, of course, is this function q then, to minimize it, I'm going to want to take the derivative and find any critical numbers. To take the derivative, though, this has two variables, and that's not good. So I'm going to have to try to rewrite this function, q, in terms of one variable only. That means I'm going to have to find something else that relates x and y together. And one of the things we haven't used in this problem is the fact that the area is supposed to be 24 million square feet. And so I can write that the area, of course, of this field, well, even though there's the three x's here, the area of the overall field, it's still just a big rectangle. The area is just length times width, which would be y times x or x times y. So I'm going to have that x times y is 24 million. And so I can solve for either x or y here. It doesn't really matter. If I solve for y, I would divide by x. So I get 24 million over x. What I can do then is rewrite this function q. So q is 3x plus 2y, but y is 24 million over x. So I get that q is 3x plus 48 million over x. All right, so that's sort of my setup for the problem. Now I can look at this idea I'm trying to minimize q, and I'm going to rewrite q with a negative exponent here. So 3x plus 48 million times x to the negative 1, right, since that x is in the bottom. To minimize this function, I want to take the derivative, so q prime. Derivative of 3x is just 3. I bring the negative down in front, 48 million. And I subtract 1 from the exponent. Negative 1 minus 1 would be negative 2. So that's going to be 3 minus 48 million all over x squared. I'm going to rewrite this as a single fraction. So 3x squared minus 48 million all over x squared. So when I look at this now, I want to find any critical numbers. That's where this is either equal to 0 or undefined. So if I set q prime equal to 0, well, q prime here is a fraction, right? This is my q prime there. And so for a fraction to be equal to 0, that only works if the numerator is 0. So I'd add 48 million to both sides, and then divide by 3. And then I'd take the square root. And so I get plus or minus 4,000. Of course, since x here is a length of a side, the negative doesn't really apply. I can't have negative length of a fence. So my only candidate really for a solution here would be positive 4,000. I could also look to where q prime is undefined. Again, since q prime is a fraction, the only time a fraction is undefined is if the denominator is 0. So that would lead to a solution of x equals 0. The problem again, though, here is x is the length of the fence. I can't have a length 0. Also, when I would try to solve for y, it would be 24 million divided by x. 24 million divided by 0 would be undefined. I wouldn't have another side. So that can't be a solution. So this q prime undefined is not really applicable. That's not going to affect us here. We found a value of x. We need a corresponding value of y. Y is 24 million over x, right? We've got that over here, right? 24 million over x is y. So 24 million divided by 4,000, we would get that y is 6,000. Notice to sort of check here, 4,000 times 6,000, 4 times 6 is 24, and then I'd have 6 zeros, and that is the area here that we wanted, 24 million square feet. So we've found a possible solution here. The question is this really a minimum for the perimeter of this, or not really perimeter, for the total amount of fencing that I have? To decide if it's really a minimum or a maximum, I want to look at this solution. X equals 4,000 is my critical number. So I want to look a little bit to either side of that critical number, a little bit less than 4,000, a little bit more than 4,000, and see what I get if I plug that into q prime. So if I look at q prime, say, of 3,500, well, if I plug that in up here, I know if I plug in 4,000, 4,000 squared, that's the 16 million. 3 times 16 million is the 48 million. That's how I get 0 in the top. If I plug in something less than 4,000, then this is going to be less than 16 million. This is going to be less than 48 million. And so when I subtract, I'm going to get a negative. So I don't really know what the number is, but I'm going to get a negative number in the top and a positive number in the bottom, which is going to be negative overall. So that means the function is decreasing when x is 3,500. On the other hand, if I put in 4,500, now I'm putting in something bigger than 4,000. So 4,000 squared was 16 million. If I put in something bigger, it's going to be bigger than 16 million. That's going to be bigger than 48 million when I multiply by 3, so the top's going to be positive. The bottom's squared, the bottom's always positive. So I'm going to get positive over positive, which is positive. So my function would be increasing at 4,500. And so I do have this situation here where my function is decreasing at 3,500 and increasing at 4,500. And here at 4,000, then where I have a horizontal tangent line, you know, that must be sort of how it's working here vaguely. It's decreasing at 3,500. 4,000, I have a horizontal tangent line because that's where my derivative was equal to 0, and then it's increasing. So it does look like this 4,000 is a minimum, and so the minimum cost occurs with two sides of y, and y was what, 6,000 feet, and three sides of 4,000 feet.